Thank you all for coming. Again, my name is Lucas Oakers. I'm a student with Dr. Schamberger, and today we'll be talking about melting dynamics and phase change composites, looking at thermal impedance and seeing how we can do that with reduced order models. So to begin, one of the main motivations within the United States, ARPA-E from the Department of Energy said that by 2030, 80% of all electricity used within the US should pass through a power electronics device, something that's manipulating the current. An example power electronic device that we'll look at is within a drivetrain of electrical vehicles, battery electrical vehicles. This is the BYD Seal. BYD has over millions of cars that they sell per year, specifically in China, and this is within the drivetrain of this vehicle. And so we can open up that drivetrain and looking at specifically the traction inverter. We have 3 half bridges and it manipulates AC/DC current. Within the power electronics module, you have DC/DC, AC/DC. Anytime you're manipulating current, we're going to be looking at these drive schedules operate over pulse dynamic loads conditions. You're never driving steady state within a vehicle. You're stopping, going, and accelerating. And so these operate over transient thermal loading conditions. This is a cross-sectional view of just a generic power electronics device with a semiconductor device on the top, base plate, and heatsink. So within the thermal network, we can look at just a single RC node resistance. If you increase in on time, put in energy to the system, you have a temperature increase. And if you keep the resistor constant, the steady state performance of the system will be the same. And underneath the transient scenarios, your capacitor is the thing that dominates. So if you increase the capacitance of the system, there's more thermal inertia within the system. So the temperature rise then is suppressed over long on times. Within these systems, you're trying to make them smaller. So you have device miniaturization that leads to lower thermal resistance and capacitance. And so then thermal engineers then either have to design bulky heat sinks that have a low steady state resistance to have larger capacitance within the system, or you're more susceptible to overheating underneath these transient thermal loads. There's larger temperature swings within the system. Moving forward, here's some more schematics of the cross-section of power electronics. There's different architecture types of adding a thermal energy system, tops, bottoms, in between heat sources. When we're talking about the junction temperature within the power electronics device, that's the hottest point within the semiconductor device. So that's the maximum temperature within the device. Then you have a heterogeneous layers of coppers, silicon nitride in this specific system. That at the bottom of that would be the case temperature. And then they add heat sinks to the system with a working fluid, whether it's a temperature or a cold plate, and that's considered the ambient temperature of the system. So when we're looking at the change in temperature, it's a change in temperature from the junction temperature to the ambient temperature. And if the ambient temperature is fixed at a constant temperature, then the temperature rise is solely a function of junction temperature. So we're looking at how we can suppress the junction temperature within the system, specifically using thermal impedance. So thermal impedance then is the difference between the junction temperature and the ambient temperature, the top hot versus the cold, normalized by the heat flux that you put into the system. And so thermal impedance then is analogous to the junction temperature rise within the system. We can model these thermal networks. If it's a single node, the sum would be 1, I guess. So you have a resistor and then exponential negative T over tau, which is the time constant of the system. That's the resistor times the capacitor. And so this is actually just a model then using this equation. And this is actually a numerical temperature rise with a single resistor.
And Lucas, what does the damage? Is it the peak temperature or the rate at which you reach temperature?
Peak temperature. That's like the limiting, in the literature, they say that's the thing that damages these devices the most is the temperature.
Thank you.
So when we look at these thermal impedance plots, so this is from the manufacturer, they give thermal impedance graphs over different duty factors. So a duty factor then would be square waves on or off. Duty factor of a half would mean that it's on half the time and off half the time, on, off, on, off. And if you go all the way down to a duty factor of 0, which would be an off time of infinity, basically it's sitting there, it's at thermal equilibrium, and then you pump in energy, and then you have a temperature rise increase. So when we look at these duty factor graphs, it's going to be the bottom line for a single pulse. Then we can look over pulse loads, and under steady state, the thing that we can see, irrespective of if there is a phase change or if there is not, if there is a phase change would be the blue line because there's a junction temperature suppression, or if there is not a phase change, at steady state, the thermal performance will be the same. Same as we saw before, it's dominated by the resistance of the system and not the capacitance of the system. So when you look at all on times, all duty factors will converge, and these plots are the maximum temperature within a single pulse is what they're plotting then if you have these pulse trends. Under transient thermal loads then, this would be an example of you have short on times and it's gone back to thermal equilibrium, been able to reset. Underneath some of these thermal loading conditions, it's not able to go back to thermal equilibrium. And that would be in this scenario that if you have a duty factor of say a half and you have some on time, it's pulsing on off, and there's residual energy within the system. So it's not able to go back to steady state, or I guess it's not able to go back to thermal equilibrium, but it is in some quasi-steady state that it's oscillating around some temperature if it's been on for a while. And this graph is the thing that would model that is irregardless of your initial temperature of the system, and you have identical heat loads being pulsed onto it, it's going to reach some quasi-steady state equilibrium maximum temperature. And underneath these transient thermal loads, so you can have, if we look at this duty factor, so it would be an on time, it would be some oscillation. And if you're between a temperature range that's unlocking or using the latent heat of the system, you can have a junction temperature suppression. And so when there is not melting, then you could have a higher maximum temperature of the system, while if the energy is going into changing the phase of the system, then you can have a junction temperature suppression. And so that's kind of the motivation in current literature out there that's going to be motivating everything within the system. So the question is then, can we use these transient thermal impedances to understand the melting dynamics actually within the system from a materials perspective within these phase change composites? The research overview that we'll look at will have four thrusts. The first thrust is, can we use thermal impedance to isolate actually this role of melting within these phase change composites? Next, we'll look at how heat transfer coefficient affects the role of melting within the composites, specifically how much energy you're taking out of the system. Then we can change the geometrical parameters of these heat sinks, the gap openings of the pores, the amount of metal you have, the volume fraction of them, the thickness of the heat sinks. Next, we can see if we can use reduced order models to model the thermal performance of these systems, and then we're trying to then see if we can predict, if we can have a model and then change these geometrical parameters or something, and then you can predict the thermal impedance after that. So we'll go into the thrust one and see if we can isolate the role of melting within these composite systems. So our generic experimental setup will be, we have a weight to decrease thermal interface resistance between the entire setup. We'll have a heater at the top, which is basically the semiconductor device. It would be turning on or off. It has relevant heat fluxes, and we'll put it through relevant thermal loading conditions. And then we attach the heat sink along to it that you can either add PCM, not add PCM. And then we add a thermal interface material, TIM, and then a cold plate to have it at a quasi isothermal temperature condition. So when you add in PCM to the system, you have sensible contributions of adding the PCM, latent contributions of the PCM, as well as it's changing the interface between the, instead of air, then it would be a metal to liquid PCM, as well as depending upon this, since this is a quasi isothermal temperature condition, it could pin the melting temperature to below the melting temperature. Even though you're pumping in energy to the system, there could be melting, but this could still be solid or liquid. So there's a thermal gradient within the system, even at steady state. Representative heat sink would be down at the bottom. These are microsived heat sinks that have sub-millimeter geometrical parameters. So they're really quite small, and they should have really high thermal conductivity within the system. And then we're going to be looking at representative thermal networks. Boxes would be a specific RC component in parallel with each other. And then when we look internally at the phase change composite, you have resistors and capacitors that are sensible with the metal and PCM, as well as a latent capacitance around the melting temperature of the system. So to begin with, again, we saw before these temperature rises. This would be just a principal thermal impedance rise when the system's empty. So you add in PCM to the system, the initial temperature is above the melting temperature of the system, so it's always liquid. You're pumping in energy to the system, and again, it has this specific time constant, has a nice time constant, but the PCM, so it has a lower junction temperature or steady state resistance, which basically means then that this is at steady state, this would be a better heat sink because the PCM that we're used in this is a paraffin heat wax. Which has a lower thermal conductivity, a higher thermal conductivity than air, which means that it has a lower steady state resistance. And then we can have a phase change happening within the system. So it's initially solid, and then we're putting in energy, and there's a temperature suppression around the melting temperature, and then it reaches the steady state. Since the thermal conductivity at solid liquid is relatively the same, these semi-converge within about 5% of each other. So what we can do then is we look at the differences in thermal impedances to see if we can kind of isolate the thermophysical properties of adding PCMs to these systems. So this would be empty again, and then fully filled, and it's only sensible heating because it's all liquid at every temperature range. And then you get the same characteristic shape, which makes sense. And you can see at steady state, the junction temperature, like thermal performance difference between the two systems. Next, when we would do be a subtraction of the empty case to the with melting case. So you have the sensible contribution of the PCM plus a latent contribution of the PCM. So those two things are coupled. And then we can take the difference between the with and without melting to decouple the role of melting within the system. So this, similar to like a DSC graph, then you would be able to get the latent energy or the thermal buffering effect of the system as a function of on time at these specific initial temperature conditions. So
can you look at that plot and say roughly when the fusion started?
Yeah, so the difference, if you take the derivative of the graphs of the thermal impedance rises, at the point of separation is at the start of melting then.
So where, on the right, where would that be?
You would take the derivative of this, but it would be about right there. And so we'll look at, I guess I'll note that this maximum temperature is actually not where melting has completed. So this is, again, we have within the system, we have a composite resistance, a composite capacitance, which is purely sensible, and then a latent capacitance around the melting temperature. And so if you're increasing temperature, the latent capacitance is either being engaged or unengaged. And that peak then would be where the contribution of the latent heat becomes less than the entire capacitance of the system. The latent capacitance becomes smaller than the sensible capacitance within the system. And if you have another question on that, I have more backup slides that we can talk about for that. So yeah, it would be the rate of change difference between the thermal impedance rises so this would be the optimal operating on time of the system. You have the maximum thermal buffering at this specific on time. So the outcome of this thrust, I guess this is a selected view of what we talked about, but it was an experimental procedures of how you could isolate the role of melting within these composite systems. It was a peer-reviewed conference proceeding, so we had an oral and poster presentation. It was an IEEE conference in Dallas. So moving on then, so the second thrust is how does the heat transfer coefficient affect the role of melting within these systems? So we'll look at just kind of a thought experiment. So we have kind of a black box, but we have a resistor and a capacitor in the system. A high heat transfer coefficient would be a small resistor between the amount of energy you're taking out and your phase change composite. So this would be a high heat transfer coefficient. Then If you increase the resistance between, you're still trying to pump out the same amount of energy, but you have a large resistor between your lane, your phase change composite, and the source that you're taking out the energy, that would be closer to the adiabatic side. So we can know then is that the steady state resistance would increase because steady state resistance is just a function of the resistors within the system, as well as if it's initially at thermal equilibrium, you're charging the capacitor, the energy now can't go out into the cold plate, it has to go into the capacitor. So we're going to have that in the back of our head that if you decrease heat transfer coefficient, the capacitor plays a larger role within the system. Research question then is how does heat transfer coefficient affect the thermal buffering effect within the system? We have the same experimental setup now, but instead of a TDIM then, how before we're adding increasing layers of polyimide tape or Kapton tape, and this is going to act as adding resistance between the phase change composite and the cold plate of the system. So we're going to be tuning this resistor and capacitor between the working fluid and the phase change composite.
Are there competing heat transfer within the system?
Like conduction or convection and stuff like that. So these heat sinks were really small, the PCM gap openings, and we should be in literature, there's a critical length scale that as you get a smaller between the fins, that the convection is suppressed. And so we are in a regime where it's purely conduction.
And do you get different heat conduction pathways within the structure?
That's exactly what we're gonna see. Yes, that it will affect the thermal pathways. Yeah. And so that's the interesting part, I guess, is that we'll look at. So we have 3 experimental configurations. Same as we saw before, is that there's with melting, without melting, it's purely sensible. And then our reference is going to be a purely sensible copper block. So it's just of the same volume dimensions, really highly conductive. So this is your model system of the most expensive, heat sink that you can have. So same as we saw before, as we decrease heat transfer coefficient, or we add increasing layers of polyimide tape or increasing the resistance of the system, the steady state resistance increases. Makes sense. Then we take the difference of these graphs. It would be the with and without phase change that we said before is a role of melting within the system, is that as you decrease heat transfer coefficient, actually the thermal or buffering effect increases. So the capacitor plays a larger role within the system. We also see that the optimal operating temperature would be the max of these graphs shifts to shorter on time. And so the role of melting then is kind of being isolated and shifted to shorter on times. And then it has a larger on time range over which the change in the delta Z is positive. So the peaks actually broaden as well. Then we can look at this. Same thing, the with melting, and then we compare it to a copper heatsink because that should be the best steady state resistance within the system. And we actually see underneath the same thermal loading conditions is that there's a crossover point that the phase change composites would be in the solid copper, and the solid lines have a lower junction temperature, specifically around the melting range. And then there's a crossover point where the copper blocks has a lower steady state resistance. So you can design these heat sinks then, especially when the engineers are constrained by low heat transfer coefficients. You can't have a cold plate or something sucking out energy within the system, is that these phase change composites actually are cheaper, but they also have a lower junction temperature over some operating on time. And that's, I guess, the new thing that is coming out of this paper. So our research question was, and we saw that the answer is that the junction temperature suppression increases with decreasing heat transfer coefficient. And we saw that these phase change composites can thermally outperform a solid copper block, which is the best highly conductive thing that we can have. Outcomes of this thrust, which it was submitted to IGHMT, and we did 1 round of edits, and this was a while ago, so we haven't heard back from the editor. So hopefully that's a good thing then, that they didn't have any more edits for us, and they'll just be accepted. So we're going to move on to thrust 3 then, is how if we flex some of these geometrical parameters, how would this affect the thermal impedance within the systems? So similar to before, we had these duty factor thermal impedance cycles. The without melting would be the dashed lines, and the with melting, when you're oscillating, there's the latent heat is being activated. There are regions over which the maximum temperature of the system is decreased. And so characteristically, these standard deviations are pretty big, and that's because these are build-to-build variations. And so you're taking apart the system and adding them back together. There's a much smaller standard deviations when you are just looking within one run and replicating that rerun together.
What about the frequency of oscillation?
Yeah, so we're looking at different frequencies of oscillations by looking at different duty factors. And so a duty factor of a half then would be on off half the time, and then a duty factor of 0.1, which would be it's on 10% of the time. So basically 1 second and then maybe off for 9 seconds, 1 second. So this is with a square wave. There's some research then if the pulse is a sinusoid instead of a square wave as well, but kind of similar things will happen after that. So what we see then is that we'll see later on, it's more clear in a lot of the other systems, but as you increase duty factor, or when could be areas, you're more common to have residual energy within the system, it's on more % of the time, the thermal buffering effect should decrease as you increase duty factor. But within these standard deviations, it kind of gets muddied a little bit. But within each system we'll look at, it's pretty clear.
So Lucas, within the system, because I was confused by that with your write-up too. Within a system, when you show standard deviation, is that just based on replicating the same material under the same boundary conditions?
So that would be build to build, unbuilding it and rebuilding it back together.
So why then I don't understand why the standard deviations are so large when you're comparing different systems than within a system if both of them involve a rebuild.
Yeah, it's you would have to have a pretty clear difference thermal performance between the systems if there's large standard deviations with unbuilding and rebuilding, because that's what we do. We'll look at different pores per inch, and that's you actually have to unbuild it and rebuild it every time you add in a new composite system, a new heat sink within the system as well. So
what do you mean, given that there's a large build to build variation, what do you think is responsible for that variation?
Yeah. So specifically the pore systems, we tried to reduce the build-to-build variation. So we glued the thermocouple with silver epoxy between the heater and the heatsink, and that should have reduced, I guess, one interface. That would be fixed. But within the pores, this is just a TIM as well, and it's not fixed. So you have a TIM, thermocouple, heatsink, another TIM. So these are kind of loose joints within the system, loose interfaces. We'll move on. I can talk more about that.
Mm-hmm.
So the research question then is, underneath identical thermal loading conditions, if we look at these pores and we keep volume fraction constant, or the ratio of liquid or PCM to metal the same, and we change the pores per inch, how large the pores are, how would this affect the melting dynamics within the system? So if we decrease pores per inch, the pores get larger because there's less occurrence of the pores per inch. And so as I guess within one system, you see that as you increase duty factor, all these systems, all the thermal buffering effects decrease. So we'll look at just the single pulse because this is the maximum thermal buffering effect. So these are single pulse data laid on top of each other. Within the standard deviation, there was basically no difference between the different pores per inches. The only one that was different was the 94 per inch. And I guess we're assuming that is the occurrence of a metal ligament is larger, or there's less distance between each ligament. What our hypothesis is that you're able to conduct the heat within the system more. And so the melting temperature range and the melting on time over which there's kind of the melting is localized. So you're getting a larger thermal buffering effect over a shorter on time. And so the magnitude is larger.
Do these all have the same density?
Yeah, so these are at constant volume fraction, constant density, same manufacturers and
Confirmed
everything.
or as stated by manufacturer?
No, they're within like 4% of each other.
So you may.
Yeah,
Let's learn the lesson, never trust a manufacturer.
yeah.
Yeah.
So we'll look at computational thrust to kind of see if we can explain some of this going on. Next, you can look at varying heat fluxes. So this is single pulses. You're off and then you just turn them on and see how the melting dynamics look at. As you decrease heat flux or the amount of energy you're putting into the system, the thermal buffering effect is broadened. As well, it takes longer, or the peak of these things shifts to the right because it takes longer to melt the PCMs because you're putting in less energy to the system. So they broaden, shift to the right. Tying kind of all together is that now these thermal engineers now have knobs that we can tune that we can look at different heat fluxes, duty factors, and on times over which there's thermal buffering, and we can change the geometries as well. So it's kind of a complex system that's also nonlinear that is tough to decouple. Next, we can look at the thickness of the composite. And so the solid lines then would be a larger composite, thicker, the distance between the hot and the cold side. What we see then within the system, then there's going to be more PCM to melt because there's more volume of PCM at the same volume fraction and same pores per inch. So the optimal operating on time increases. It shifts to longer on times, as well as the overall thermal buffering effect of the system increases, which makes sense. Outcomes of this thrust, pretty blank paper, but we have the computational or the experimental thrust, I guess, done with this. And then we're going to look at how we can try and model this computationally in the later thrusts.
So what are the computations? What are you trying to answer with that?
What are the melting dynamics of the system? Is this 1D heat transfer, 2D heat transfer? Are we within length scales of a regime where 1 to 2D heat transfer, or are these pores large enough that maybe there is convection within the system and now we're not in a regime where that convection is suppressed?
So just to clarify, because you have a lot of the same sort of plot.
Yeah.
So when we're looking at them, when you're showing the standard deviation for the 37 PPI material on the right,
Build to build.
all of the other cells also have similar sort of standard deviation.
I think it would be, because the only standard deviation difference would be the building, I'd say.
Yeah. So if that's the case, so if the bounds for the 37 PPI are representative of what they would be for the others, do you actually have a statistical significance between 20, 37, 58?
I didn't run a statistical thing, but
Just eyeball what.
I mean, it's close. It would only be over a short on time for sure. And I think that's why we are gonna have to go to the computations, and we're modeling these systems in a 2D sense to see, I guess, what's going on in the system, what pores are melting and how long it's taking to melt and stuff like that.
Can you state the question again?
Yeah, I'm looking at the plus minus 1
35.
standard deviation bounds for the 37 PPI and imagining similar standard deviations for all the others, right? Just trying to understand if there's a signal there
Between
or
this
if
one
that
and
noise.
these. Yeah.
So
So next we'll look at kind of what we've done to model some of these systems, and then what we're planning to do for future work. So when we're looking, this is part of Dr. Phelps's paper, so I guess this is why we're putting it in as well, is that there are regimes under which similar to your question before, the convection is suppressed, as well as the melt front actually goes from a 2D melt front to a 1D melt front, is if you get to small enough thin pitches. And so The issue then is if you're trying to model everything as a 2D, like in ANSYS or even 3D or something like that, or in COMSOL or ANSYS, is that these computations take a really long time. So if you're going to sweep across pore sizes or something like that, it's really computationally expensive. So first, we're trying to see if there's some validity regimes over which we can do lower order models and how these lower order models can predict thermal impedance of the system. Similarly, kind of same concept as if you are increasing the microstructure size of these systems, we go from 1D to 2D and then to 3D heat transfer within these systems. So we're going to try and see are there some broader validity regimes, both for pore sizes to thermal physical properties, the heat fluxes, thermal loading conditions over which we can do these lower order models and actually replicate thermal impedance within the systems. So we can have a generic phase change composite and how you would look at the fidelity of these systems and see if they're accurate or not. Is that then you can do depth profiles and then you can take the average at a specific depth, find the standard deviation as well, and try and overlay them on top of each other and see which ones are close to either experimental data or higher fidelity 2D simulations. Research questions then are kind of what fidelity of reduced order models are needed to capture the thermal impedance of the systems, and can we take 3D experimental data to find a 1D to represent the thermal impedance rise of these systems in a 1D resistor and capacitor function. How do we get then? We're going to go from 0D all the way up to 2D models. So how would we get it to a 0D model? Is we would take the thermal circuit, collapse everything on top of each other into a 0D model. But then you say, what do we do with the capacitor of the system? And similar to this, we just had a generic heat transfer equation. And then you can find the resistance of the system. Again, is the steady state resistance found experimentally. So this is experimental input. The latent capacity of the system can be found through DSE. So that's just a thermal physical property and standard deviation. And then you can use the apparent heat capacity method, which is modeling the capacity of the system through a Gaussian profile. And we use the skewed Gaussian profile to model the temperature rise or the capacitance of the system.
Is that actual DSC data?
So this in the paper, it wasn't a heat capacity data. I just took the latent heat of the system and then I was able to back calculate out a representative heat capacity, but it's not standardized or anything like that. It was just the reviewers were confused by this, and so they just wanted to kind of look at what it would look like. And so this is just from DSC data, but it's not using the standard defined heat capacity.
So you made some assumption about the width of the.
Yeah, I took the standard.
We are calling this a skewed Gaussian.
Yeah, so we took the standard deviation of the using the DSE, but then we did skew it, and that was a fitting parameter that we said.
How do you determine the skewness?
But we overlaid it on top of the experimental data and kind of looked at how much we need to skew it. Yeah, it was just an experimentally fitted parameter.
Okay.
Yeah.
So when I'm just looking at DSC data, later you're going to tell us that you're modeling with a mushy zone.
Yeah.
Is this not a congruent melting system? Because it sure looks like a pretty sharp peak.
Melting peak.
Yeah. The skewness would be pretty small, but some people do model. The reason why we even add the skewness is because other people have done it in the past, and so they said that you're able to.
I mean, what is the PCM space?
Hexadecane.
And if you go decimally slowly, 0.001 C per minute.
Yeah.
Would you expect a finite width to your peak, or would it be a delta function?
There's I'm not the expert on the DSC, but yeah, there's two different models of the system. If you increase scanning rate, the onset of melting shifts. But I believe that this is one that, irregardless of scanning rate, that the peak should be at the same point.
You're talking about position, but what about the width?
I think width does change. Is that right? It would have to change, I guess, if if the magnitude changes. But the onset of melting doesn't change, I guess.
So no, my intuition says you're at 0 going to be slow. It's an activated process, but you're giving it infinite time to occur. It's some lower temperature. I don't know.
So,
Well, I guess, yeah, so the peak, the width would change, but specifically this onset of melting shifts if you have like binary components of the system, and so that wouldn't happen if that's your question in the system.
Well, I mean, I think the question was, is it congruent melting? That was the original question, right? So first, let's just answer that. Does it melt congruent? What's the definition of congruent?
That's why I don't actually, I would, does that mean that the melting temperature is fixed, irregardless of scanning rate?
Yeah.
it just means that the solidus and the liquidus are the same temperature.
Yeah,
There is no mush.
there's no mushy zone. I guess I would say yes of this system.
Yes to which?
It's congruent melting.
But the thing about paraffins, they always melt over a finite range of temperature.
Because of the chain lengths. So the chain lengths are random. And so you do get actually a mushy zone. Yeah. And again, this is a 0D model, so we're assuming that the temperature within the entire system is the same. And so there's a lot of assumptions when you have to go to 0D. And when we initially did this, it was actually fairly surprising that this was more of a qualitative. We were trying to figure out why does this thermal buffering effect changes heat transfer coefficient, and we're able to model the trends within the system, specifically with the 0D model. So we thought it was useful, even though quantitatively, some of these regimes where it didn't model it quantitatively, I guess.
Sorry, there's a lot of information going on here. What was the DL5?
So these are, okay, I guess, yeah. So at the beginning, this is adding layers of Kapton tape. So between the pitch-inch composite and the cold plate, we're adding layers of resistors. We're increasing the resistance of the system, the total resistance. And so you're not able to suck out as much energy within the system. And so the thermal buffering effect increases.
So how would this change if you had a PCM with a much higher latent heat and lower conductivity?
Well, if you're assuming still 0D heat transfer, so that would, then the thermal buffering would increase of the system. But then you start to get in regimes where it's never going to be 0D. And the reason why we're able to say it's 0D is because the distance between a really highly conductive node is so small that the heat is able to pass from the hot to the cold side, as well as the lateral thermal spread's really small within the system. And then so you'd approach areas where it's not 1D heat transfer, and then experimentally, like if it was pure, say this composite was pure PCM, it was just 100% PCM, it's never going to have a lower junction temperature experimentally than the copper block, even though it has a really high capacitance. It just the way you can't wick away energy from the heat source quickly enough. So next, we created code to do a 1D model, and so this would be the enthalpy porosity method with a mushy zone, and you can model the mushy zone using a linear interpolation between the solidus and liquidus temperatures of the system. So the heat capacity, the temperature, and then how much is melted within the system. Just doing a node by node analysis using the same heat equation to begin with.
I'm confused. Why on that legend, why is your reduced distance 0 not corresponding to the heat spreader in your PCM bottom not corresponding to the bottom?
I guess this would be a TIM thermal interface material, and so the thermocouple's on the top of the TIM.
Yeah.
So
but why is your 0 so high, so much higher than the heat spreader on the legend?
Is the legend to scale?
I
Is the
guess.
scale to scale?
I guess this scale is, the colors are correct, but yeah, I guess you could shrink the legend smaller.
Point to where 0 is on your.
I mean, 0 would be, I guess, here.
Okay,
And
so
1
the
would be.
scale is nothing.
Yeah.
The
Yeah,
scale
the
is
scales, I
nothing.
guess I should have put shrunk
I
the
got it.
scale so it was the same height. Yeah,
I'm less confused. Thank
yeah,
you.
sorry. I understand. The colors are correct though. So next, this is really, I guess, where there's new literature is how can we use these resistor and capacitor networks that are in a 1D sense with the phase change process. So this is kind of getting into the newer territory is that just thought experiment is we have this heterogeneous composite, we have heat in, heat out. We know that it can be modeled through resistor and capacitors in parallel with each other. That's what we saw before. And so this is called the Foster network. Is what it does is it takes the different time constants. We have different RC nodes through a heterogeneous composite. We can look at it and do a Fourier analysis or a Fourier transform.
Do we know that?
What?
That you can model a composite PCM using a Foster network?
I'll show that we can, yes, and we have.
But this is, what is that, something that is extensively used out there, or,
Not with melting. So,
and why not? What's the concern?
oh, I guess yes. Send me up. So we'll talk about that. Because these are passive linear elements and the phase change process is non-linear. And so that's, I guess, why these linear distributed non-uniform networks have never been used for the phase change process before. Because if the network is dependent upon the initial temperature of the condition. If you can model just a semiconductor stack, the thermal performance or the thermal impedance rise is going to be the same irregardless of the starting temperature. If you have the same heat flux, you're still going to have the same junction temperature rise. So that's, I guess, why they've never been used to the phase change process. But we're going to
and Lucas, more usefully, independent of the applied power. So once you normalize by power, the thermal rise goes accordingly. You have an LTI system, right?
Yeah.
So not just initial temperature or ambient, right? You can change the ground point on the right-hand side. That's your ambient temperature. But you can also change the applied power. The transfer function is still the same. So Z thermal is your transfer function.
Yeah. So you can model it with the Foster network, which is this first one. And then you can do a infinite sum of this basically, and then you can get a continuous time constant spectra of the system. However, these specific capacitors, you can change the values of them when you're starting the energy. Basically, all the capacitors are charging at the same time. There's no physical meaning but of what that capacitor value is. And so we're going to try and do a transform then between a node to node capacitor and a node to ground capacitor. And so they do a Foster to Cauer transform of the system, doing a numerical manipulation. Once you do a node to ground capacitor and this Foster to Cauer transition, so this would be considered a Cauer network, the specific capacitance and resistance values, if you plot the thermal one port from the source to the drain, the actual values of this ladder represent the specific capacity and resistive elements within your thermal network. So these can be mapped physically onto the system. So you can look at maybe the first slope can correspond geographically or actually geometrically onto the system. And each slope then would be a different layer within their system. And so can we apply this to the phase change process? And this thermal impedance, the Foster Cauer network is, there's commercial applications of this, but we made our own because we don't have the software or anything like that. And these were validated by using the Army Research Laboratory's data. And so these are correct. And so how we read these graphs then is the empty case, this would be purely sensible. And then again, this red case would be purely sensible. The same heat sink then during the melting there's an increase in capacitance within the system. And that's basically what we saw before. The parent heat capacity method is that around the melting temperature, you have an increase in capacitance of the system, and then you would traverse along more resistance. And then again, the farthest distance from the thermal one-port source is a cold plate, which basically would be an infinite capacitance because that's pinned at a constant temperature. So that would be represented by an infinite capacitance within the system. So we are able to get a one-dimensional kind of a depth profile of the thermal network within the systems. So the point then is, can we put these thermal Cauer networks and can we look at it with a phase change process? And can we use it to replicate the thermal impedance at all temperature conditions? The next fidelity model that we can look at is anti-simulations using, so these are the pore sweep. We can have a cross-sectional view of it. And I'm currently doing different convergence models and trying to make sure that the models have converged and that we're actually getting the correct output temperatures of the system. So I'm working through that right now. The point then is we've looked at a whole bunch of different fidelity models. There should be regimes over which each model is accurate depending upon geometrical parameters, thermal loading condition, and thermal physical properties. So this is the proposed kind of new work that we're going to do, is that we're trying to add a node to ground capacitance of the system. So if we look at the thermal impedance of the system, we saw before then to Dr. Schamberger's question, is that when you change the initial temperature, the thermal buffering on time and the magnitude of this would change. And so can we use that to our system? And so these are schematics, I guess. So this is the only experimental data. And so this would be considered a purely sensible case. And then you go around the melting temperature. You're going to have an increase in capacitance early on. And then if you go at different RI values or resistor values, which would be in the distance direction from the heater to the cold plate, it kind of looks like an envelope, and it would be a Gaussian profile. And then at that specific resistor value, at this RI, you can plot what the magnitude of this capacitance is. Then as you go lower to the melting, underneath the melting temperature, 25 then, I guess about 7 degrees should have the maximum thermal buffering effect within the system. And so again, as you go along the envelope from RI, from the source to the drain, it looks like a Gaussian profile. And then at this specific RI value, we can plot the magnitude of that. And again, it's going to look like a Gaussian profile. However, then is you can make a system really, really cold. And then even though you're pumping in energy to the system, it's never going to melt. So it's always going to go back to the sensible case, purely sensible heating. So the envelope's going to close again, and then we're going to be able to get a Gaussian profile at that specific resistance value. So what is the point of this then? Is we'd like to model the latent capacitance of the system at every single RI value. So we take this graph, looking at it, this is a projection along the one-dimensional direction. And so if we would take that, then going from the source to drain, you can have a representative apparent heat capacity in the one-dimensional direction instead of the zero-dimensional direction that we had before. So we proposed this to iTherm again, and it was accepted. So we gotta write the paper, I guess, and I gotta do the work. And we're currently doing the experimental data to get the information for this thrust. And then we'll look at, again, we're doing these ANSYS simulations, doing different pore sweeps, modeling them. So this is an output of the ANSYS simulation. And how the point of it then is we looked at the thermal impedance. It didn't, again, within the standard deviations, we can't tell much what's going on. Can we use ANSYS to look at individual pores and kind of look at the melting dynamics within the system? So there should be regimes. After all this is done, we should be able to combine all the works and then make some metrics over which some 0D, 1D structure functions or 2D models are valid within these systems. So the Gantt chart of this would be initially the iTherm proceedings is due in January. So we'll do the structure functions first. Then I'm currently working on ANSYS simulations. Then after we have then all the reduced order models done, we'll be able to overlay them, hopefully write a paper on that, and then go towards dissertation. So I'd like to acknowledge our partners at the Army Research Laboratory and University of Maryland, Adam and Michael and Rachel. So thank you.